I must state at the very beginning of this broadcast that this is an AI-generated analysis. Welcome, and thank you for joining us for this comprehensive analysis and detailed technical review of Brian Greene's remarkable book, The Elegant Universe.
It is a pleasure to be here with you today to discuss this material.
Our mission today is to systematically explore the mathematical framework that seeks to stitch together the fundamental laws of the cosmos. We will proceed at a measured, deliberate pace, ensuring that these highly complex physical concepts remain completely accessible to you.
Indeed, the foundational premise of this text rests on Albert Einstein's final, unfulfilled pursuit. For the last 30 years of his life, Einstein sought a unified field theory.
He envisioned a single, elegant, logical framework that could describe all the forces of nature.
He did not succeed in his lifetime, but modern physicists now propose that superstring theory might be the exact mathematical framework Einstein was looking for.
To appreciate the magnitude of this unified framework, it is helpful to first examine the quiet dilemma that has troubled modern physics for over half a century. Modern physics is supported by two foundational pillars.
The first pillar is Einstein's general relativity. This provides the mathematical framework for understanding the universe on a macroscopic scale, stars, galaxies, things of that nature.
And the second pillar is quantum mechanics, which governs the microscopic realm of atoms and subatomic particles. Both of these frameworks are astoundingly accurate when applied to the respective domains.
The dilemma arises because they are mutually incompatible. When you attempt to combine the mathematics of general relativity with the mathematics of quantum mechanics to describe something that is both incredibly massive and incredibly small,
Such as the center of a black hole.
precisely, the equations completely break down and yield impossible answers.
If general relativity and quantum mechanics are both practically flawless in their own arenas, how exactly did physics arrive at this profound incompatibility? It seems counterintuitive that the universe would operate on two entirely different rulebooks.
The progression of modern physics has always been driven by resolving seemingly impossible conflicts between established theories. The incompatibility between general relativity and quantum mechanics is actually the third major conflict in a historical sequence.
To understand how we arrived here, we can trace the first two conceptual revolutions. The first major conflict emerged between Isaac Newton's laws of motion and James Clerk Maxwell's laws of electromagnetism.
Newton's laws implied that velocities are simply additive. If you move fast enough, you could theoretically catch up to a beam of light and see it stationary next to you.
However, Maxwell's laws of electromagnetism stated that the speed of light is an absolute constant and can never be caught. Einstein resolved this first conflict by developing the theory of special relativity.
Which completely rewrote our understanding of how space and time operate.
Special relativity truly forces us to abandon our everyday intuition. Picture a scenario at a drag strip with two observers, Slim and Jim. Slim is driving a high-speed vehicle down the track, while Jim stands stationary on the sideline.
Jim uses precise instruments to measure the elapsed time of Slim's run and the exact physical length of Slim's vehicle as it passes by at very high speeds.
Before Einstein, the assumption was that both observers would measure the exact same elapsed time and the exact same vehicle length, regardless of their relative motion.
However, special relativity proves that because Slim is moving relative to Jim, Jim will actually measure a slightly shorter elapsed time and a slightly shorter vehicle length than Slim measures from inside the car.
The difference at ordinary speeds is a tiny fraction of a unit, but it is physically real.
Yeah.
This fundamental discovery proves that space and time are not absolute rigid structures. They are entirely malleable constructs.
Their measurement depends entirely on your relative state of motion, and resolving that first conflict immediately triggered the second historical conflict.
Special relativity established a hard, universal speed limit. Nothing can travel faster than the speed of light.
But Newton's long-standing theory of gravity relied on the concept of instantaneous influence. Newton believed that if the sun were to suddenly disappear, the Earth would instantly fly out of its orbit.
Implying that gravity travels infinitely fast across vast distances. Einstein resolved this second conflict by developing his general theory of relativity. He discarded the idea of an invisible gravitational tether.
Instead, he proposed that space and time are woven together into a unified fabric called spacetime. Massive objects rest upon this fabric and create deep curves or warps within it.
When the Earth orbits the Sun, it is simply rolling along the natural curved valley created by the Sun's immense mass. Gravity, therefore, is not an invisible pulling force.
Gravity is the physical warping and curving of the space-time fabric itself in response to mass and energy.
General relativity provides an incredibly elegant picture of the cosmos, but it comes with a strict mathematical requirement. The equations of general relativity only function if the space-time fabric is a smooth, gently curving geometrical surface.
This specific requirement brings us to the core of the third conflict. When we shift our focus from the macroscopic universe to the quantum framework, that required smoothness entirely disappears.
Quantum mechanics is dictated by Werner Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the precise position and the precise velocity of a particle.
This inherent uncertainty means the microscopic realm is not peaceful or smooth. It is a chaotic environment where energy and matter are constantly erupting into existence and immediately annihilating each other.
That microscopic frenzy is the exact source of the incompatibility. To understand the scale of this conflict, we have to examine the universe at the sub-Planck length.
The Planck length is 10 to the negative 33rd power centimeters. To put that unimaginably small scale into perspective, if a single atom were scaled up to be the size of the entire observable universe, the Planck length would be roughly the size of an average tree.
At this scale, human intuition is entirely useless. We can think of the space-time fabric like a highly detailed dot matrix photograph. From a macroscopic distance, the photograph looks perfectly smooth and continuous.
General relativity operates beautifully at this distant perspective, but when you examine the photograph closely, you see it is actually composed of discrete, separated dots.
When physicists examine the space-time fabric at the sub-Planck length, the smooth geometry predicted by Einstein vanishes completely. At this scale, you encounter what the physicist John Wheeler called quantum foam.
The violent microscopic fluctuations of quantum uncertainty create a turbulent, boiling environment. This quantum foam utterly destroys the smooth geometrical structure that general relativity needs to function.
When theoretical physicists attempt to combine the mathematics of the smooth macroscopic fabric with the violent microscopic quantum foam, the equations yield nonsensical answers.
They produce infinite probabilities. And an infinite probability in physics represents a total breakdown of the mathematical model.
If the standard model's reliance on zero-dimensional point particles is what triggers these infinite mathematical breakdowns at the quantum level, the solution requires completely abandoning the concept of a coin particle.
This is the precise paradigm shift that superstring theory introduces to modern physics. The standard model categorizes the fundamental building blocks of matter quarks, electrons, neutrinos, as perfectly spherical, zero-dimensional dots.
They have no internal structure and no spatial dimension whatsoever. String theory replaces these zero-dimensional points with one-dimensional, infinitely thin vibrating filaments.
These filaments are called strings, and their average length is roughly equal to the Planck length.
Shifting from point particles to one-dimensional strings creates a fascinating cosmic symphony. In the standard model, the physical properties of a particle, such as its mass or its force charge, appear arbitrary.
In string theory, these properties are determined directly by the specific vibrational pattern of the string. Picture a violin string. Depending on how it is plucked or bowed, it can vibrate in different resonant patterns to produce different musical notes.
In string theory, the fundamental strings act in the exact same way. One resonant vibrational pattern produces the mass and force charge of an electron.
A completely different vibrational pattern produces the specific properties of an up quark, or a photon, or a theoretical graviton. The entire universe is composed of the exact same fundamental strings, simply playing different notes.
This elegant conceptual shift is also the exact mechanism that cures the mathematical infinities plaguing the merger of general relativity and quantum mechanics.
The infinities arise precisely because point particles have zero size. Having zero size allows them to endlessly probe the disastrous, violent fluctuations of the quantum foam at the sub-Planck scale.
Strings, however, are one-dimensional and possess a physical length. Because they have a spatial dimension, they cannot physically interact with distances that are significantly smaller than their own length.
The extended nature of the string effectively smears out the violent sub-Planck scale quantum jitters.
We can visualize this smearing effect by imagining drawing your bare hand across a highly polished granite countertop. To your human fingers, the surface feels perfectly smooth and continuous.
However, if you were to look at that exact same granite surface under a powerful microscope, you would see that it is actually composed of highly irregular, bumpy, discrete grains.
Your fingers are simply too large to feel the microscopic bumps. The physical size of your hand smears out the rough microscopic details.
In the exact same way, the fundamental strings are simply too large to detect the disastrous subplanck fluctuations of the spacetime fabric.
This smearing mechanism allows the mathematics of general relativity and quantum mechanics to coexist peacefully without producing infinite probabilities. At the time of this discovery, physicists actually found 5 completely different mathematical versions of string theory.
While this smearing mechanism offers a brilliant resolution, string theory introduces mathematical requirements that severely challenge our perception of reality. The most astonishing requirement is the existence of extra-spatial dimensions.
We are intimately familiar with 3 extended spatial dimensions. The idea of hidden dimensions was initially proposed in the 1920s by the Kaluza-Klein theory.
Which suggested that extra dimensions could exist all around us if they were curled up to an unimaginably small size.
Picture a long garden hose stretched out across a canyon. If you look at the hose from a mile away, it appears to be a simple one-dimensional line. You can only specify a location along its horizontal length.
However, if you walk up to the hose and examine it closely, you realize it also has a circular girth. It has a curled-up second dimension.
An ant crawling on the hose can move back and forth along its length, but it can also walk around its circular dimension. String theory proposes that the fabric of our universe is exactly like that garden hose.
It possesses large extended dimensions that we freely move through, but it also possesses additional curled-up spatial dimensions that are simply too small for our current experimental equipment to detect.
These extra dimensions are not a matter of philosophical preference. They are a strict mathematical necessity. When physicists first calculated the probabilities of quantum events using the mathematics of string theory in only 3 spatial dimensions, the equations yielded negative probabilities.
A negative probability is a physical impossibility. The mathematics only yield acceptable, positive probabilities if the strings vibrate in 10 dimensions, 9 spatial dimensions, and 1 dimension of time.
This dictates that there are 6 extra spatial dimensions hidden all around us. Physicists have determined that these 6 extra dimensions are curled tightly into highly complex, multidimensional geometric figures known as Calabi-Yau shapes.
The physical implications of these hidden Calabi-Yau shapes are profound. As the microscopic strings move and vibrate, they are essentially vibrating through the internal geometry of these curled-up extra dimensions.
The precise geometric shape of the Calabi-Yau space dictates and restricts the allowed resonant patterns of string vibration.
Because the vibration of the string determines the properties of the particles, the specific geometry of these hidden extra dimensions fundamentally determines the physical properties of the universe we observe.
This leads to what physicists consider the ultimate $64,000 question. Out of tens of thousands of mathematical possibilities, which specific Calabi-Yau shape accurately represents the hidden dimensions of our universe?
Answering that question would provide an enormous experimental signature for string theory. The mathematical equations demonstrate a direct correlation between the geometry of the Calabi-Yau shape and the observable universe.
For example, the number of multidimensional holes present in a specific Calabi-Yau shape corresponds exactly to the number of particle families that will exist in that universe.
We know from extensive particle accelerator experiments that there are exactly 3 families of fundamental particles in our natural world.
If string theorists can discover the underlying mathematical principle that naturally singles out a Calabi-Yau shape with exactly 3 holes, it would provide a powerful postdiction, mathematically explaining a known feature of the natural world from first principles.
The implications of these curled-up dimensions become truly bizarre when we examine the rules of quantum geometry. Because a fundamental string is a closed loop, it interacts with these hidden circular spaces in ways that zero-dimensional point particles simply cannot.
A string can interact with a curled-up dimension in 2 distinct ways. First, the entire string loop can slide along the circular dimension, executing typical vibrational motion. Physicists refer to this as vibrational energy.
Second, because the string is a flexible, closed loop, it can actually wrap itself around the circular dimension, much like a rubber band stretched tightly around a cylindrical tube. Physicists refer to this as winding energy.
The interaction between vibrational energy and winding energy leads to a remarkable physical realization known as the R and 1 over R duality.
Suppose we assign the radius of a curled-up circular dimension, the mathematical value of R. The total energy of a string operating in this space is a combination of its vibrational energy and its winding energy.
The string theory formulas reveal an absolutely perfect mathematical symmetry. If you calculate the total physical properties of a universe with a very large radius of r, and then you calculate the physical properties of a universe with a very small radius of 1 divided by r.
The resulting mathematical answers are entirely identical. The numerical values for the winding energy and the vibrational energy simply swap places in the equation.
Because the total physical properties are exactly the same in both scenarios, a universe with a massive radius of r is completely, physically indistinguishable from a universe with a microscopic radius of 1 divided by r.
This duality leads to a staggering conclusion. There is an absolute minimum limiting size to the universe. If a dimension attempts to collapse below the Planck length, the physical reality is exactly the same as if the dimension were expanding.
The concept of a universe collapsing down to an infinitely small point is completely replaced by a universe that naturally bounces back from a minimum allowed size.
This deep understanding of quantum geometry facilitated another major breakthrough regarding the stability of the spacetime fabric. In the framework of general relativity, the fabric of spacetime can bend, stretch, and warp under extreme gravity, but it is fundamentally prohibited from tearing.
A tear in spacetime would represent a catastrophic failure of physical laws. However, string theory calculations, famously debated in the Institute for Advanced Study Tea Room, prove that the fabric of space can actually tear and repair itself without destroying the universe.
This phenomenon is called a flop transition. Physicists utilized a highly complex mathematical technique called mirror symmetry to track the evolution of a Calabi-Yau shape as its geometry undergoes a spatial tear.
Through these mirror symmetry calculations, physicists proved that while the geometry of the space undergoes a violent tearing and repairing process, the extended nature of the strings protects the surrounding universe.
The strings effectively isolate the tear, ensuring that the physical properties of the particles remain perfectly well behaved. This brilliant mathematical proof demonstrates that physics continues to function smoothly even when the very fabric of space rips apart.
All of these isolated discoveries eventually culminated in the second superstring revolution, which profoundly changed the landscape of modern physics in the mid-1990s.
Prior to this revolution, progress in string theory was severely limited by an approximation technique called perturbation theory. The exact mathematical equations of string theory are incredibly difficult to solve.
To make progress, physicists relied on perturbative approximations. These approximations depend on a value called the string coupling constant, which dictates how strongly individual strings interact with one another.
The critical limitation is that perturbative approximations are only mathematically reliable if the string coupling constant is a very small number. If the constant is large, the approximations fail completely.
Because theoretical physicists were forced to rely on these limited approximations, they seemingly discovered 5 completely separate, equally valid mathematical versions of string theory.
This caused massive frustration in the physics community. Einstein's goal was a single, unified theory, not 5 different ones.
However, by discovering mathematical techniques that allowed them to venture beyond the weak coupling perturbative approximations, physicists uncovered a grand unification.
They proved that the 5 seemingly separate string theories are actually just 5 different mathematical viewpoints of one single overarching framework. This master framework is called M-theory.
M-theory reveals 2 monumental new features about our universe. First, it requires the existence of an 11th dimension.
The previous assumption that string theory required exactly 10 dimensions was revealed to be an artifact of the limited perturbative approximations. When the coupling constant is increased, a hidden 11th dimension physically expands.
Second, M-theory reveals that one-dimensional strings are not the only fundamental ingredients of reality. The expanded framework includes 2-dimensional surfaces called membranes, as well as higher-dimensional objects collectively referred to as branes.
This vastly expanded mathematical framework allowed physicists to finally decode extreme cosmic phenomena, most notably the internal structure of black holes.
By utilizing the advanced mathematics of M-theory, physicists demonstrated a remarkable phase transition regarding black holes. They show that a spatial process called a conifold transition can actually transform a massive black hole directly into a massless elementary particle.
In the framework of string theory, a black hole and an elementary particle are not entirely different entities. They are revealed to be 2 different physical phases of the exact same underlying stringy material.
This profound connection is directly analogous to the way solid ice and liquid water appear to be completely different substances, yet they are simply 2 different phases of the exact same underlying molecules of H2O.
This deep structural understanding of black holes naturally extends into the broader realm of cosmology and the origins of the universe. The Standard Model of cosmology describes the origin of the universe through the Big Bang theory.
It posits that approximately 15 billion years ago, the entire observable universe erupted from a singular point of infinite density and absolute zero size.
However, the mechanics of string theory fundamentally prohibit this impossible singularity. As we established earlier with the R and 1 over R duality, string theory imposes a strict, absolute minimum limiting size to the universe.
The universe physically cannot shrink to a zero-size singularity. This naturally resolves one of the most critical mathematical breakdowns of the standard physical laws, providing a framework where the birth of the universe does not require an impossible point of infinite density.
As we look to the cutting edge of theoretical physics, the implications of M-theory lead to truly fascinating cosmological speculations. The physicist Lee Smolin, for example, has proposed a comprehensive multiverse theory based on these mechanics.
In his framework, universes literally give birth to new, separate universes through the core of black holes.
Furthermore, the fundamental parameters of the particles and forces in a surviving universe would naturally undergo a process of cosmic evolution, becoming optimized for the production of more black holes.
This speculation proposes a logical, evolutionary mechanism for why our specific universe possesses the highly specific physical constants that we observe today.
Another deeply profound theoretical speculation comes from the mathematician Alan Kohn. His highly advanced work involves a field called non-commutative geometry, which focuses on the fundamental objects within M-theory known as zero-branes.
This specific mathematical framework points toward a primordial realm of the universe where our conventional macroscopic notions of space and physical distance simply melt away and cease to exist.
It suggests a spaceless and timeless primordial state that may have existed before the expansion of our current universe began.
That concept presents a final, highly provocative thought for you to consider long after this analysis concludes. I challenge you to try and imagine a reality where space and time are not fundamental, foundational ingredients of the universe at all.
Imagine a scenario where the space you move through and the time you experience are merely convenient illusions.
Consider that they are concepts that only emerge at large, macroscopic scales from a much deeper, entirely incomprehensible state of interacting zero branes. It is a concept that fundamentally forces us to question the very fabric of our perceived reality.
This concludes our comprehensive analysis of the material. To all the friends of the show listening today, we strongly recommend that you acquire and read the actual book, The Elegant Universe by Brian Greene, to explore these brilliant mathematical concepts firsthand. We encourage you to subscribe to this broadcast so that you never miss a detailed technical review of vital scientific literature. We wish you a great day.